Good afternoon, ladies and gentlemen. My name is Andrea Penna. I'm a professor of structural engineering at the University of Pavia. The topic of today's webinar is nonlinear time history analysis of unreinforced masonry buildings. As we are used, this kind of analysis method is not commonly adopted, and somehow we are also used to think that these kind of structures, reinforced masonry structure, are often characterized as non-engineered structures. So we think that this is probably not even feasible or not practical using commonly available modeling strategies. But what I'll show you later on probably will change your mind, at least partially. The analysis methods we know for seismic assessment of structural response of buildings are different. Normally codes, design codes or standards include linear, static and dynamic model methods, nonlinear static analysis methods, which are considered the state of the art of the seismic assessment of existing structures. And normally codes allow for the use of nonlinear dynamic analysis, but they normally give just limited information on these analysis methods and procedures. Linear analysis is basically a strong simplification. We all know that a complex behavior as the one which is reported in the drawing on the left can be hardly represented by something which is similar to the behavior represented by the linear force displacement, which is a relationship which is reported on the right. If you look from this simplification, we hardly tend to believe that the model on the right is the right model to represent what happens in the system represented on the left. But this is something that we normally do to some extent. Linear analysis methods have a lot of advantages. The simplifications, as we all know from structural dynamics, are many. We can, for instance, use the modal decomposition, which allows to represent the motion of the structures using the superposition of different local modes that can be activated in the response of complex structures. Another advantage is that also the representation of seismic input can be simplified and generalized somehow. The introduction of response spectrum is a big advantage and a big simplification that actually builds on this linear world paradigm. And in the linear world, we can shift the problem into the frequency domain with a number of advantages. Well, response spectrum has inherently other simplification. The first one is that you normally refer to a code response spectrum with a standard shape. and also that we use a constant viscous damping, constant for all the periods for which we represent the maximum effect by means of the response spectrum, and this viscous damping coefficient represents the energy dissipation capacity of the system. So even when we use a small value for this coefficient, we are, let's say, linearizing also the energy dissipation part. Another characteristics of the linear methods is that in this simplified analysis, we normally use a force-based approach, which means that we use this method to compute internal forces, actions acting on members, on specific portion of the structure, and comparing the acting force with the strength. So this is characteristics of this kind of this type of analysis. And okay, part of the energy dissipation is represented by the viscous damping, but the significant nonlinear response that we have seen at the beginning in the starting discussion about the nonlinear complex system, the nonlinearity of the system is all, say, hidden in the force reduction factor. Eurocode call it behavior factor, and letter Q, which is a factor reducing the spectrum ordinates. It is typically constant. It depends on several characteristics of the building, but all in this value again we are hiding in a conventional safety verification the damage that we accept occurring in the structures, and assuming its additional energy dissipation helps in reducing the ordinates of the spectrum. It is a very practical method, but again holds several simplifications. So we can summarize some of the main aspects of linear analysis. The first one, of course, is that we use linear models with constant stiffness. This allows many advantages, including the linear superposition that we can use also in the case of the simulation of the dynamic response of structures. And the response is computed based on the elastic response spectrum with an assigned damping specified for the structure we are considering. But actually, for the family of structure we are considering, not specifically for the one we are analyzing, and the force-based safety checks, which establish a framework, allow in the end to use in a post-processing procedure a computation of displacement or drift demand, but they hold on other assumptions that are done in the parameters of the damping or the Q factor we have used. And then there is this Q factor, which is a factor allowing for the reduction of the seismic action. and it is something that is a proxy of the system activity and its effect in reducing the in producing an equivalent reduction of the forces. All these aspects are, say, characteristics of the analysis method, which basically represent both advantages and some limitations. Intrinsic limitation of linear analysis include its in linearization of an inherently nonlinear phenomenon characterized by cracking, yielding, friction, depending on the structures, and in terms of lateral response, it is also affected by stiffness and strength degradation, pinching, cyclic effects in general, cumulative damage that are not accounted for in these linear methods. Another limitation is the approximate representation of the failure mechanisms and the damage modes and their sequence and progression of damage, and the combination of all these effects, and which is somehow simplified, as well as irregularity in planning and elevation and accidental torsion, are often treated in a simplified manner, or in general they include some simplification. In particular, when we deal with a system which is exploring its nonlinear behavior in some aspects, and we assume that for other aspects it's still behaving in a linear way. As we were saying before, displacement estimates also depend on the choice of the effective stiffness, which is an elastic stiffness reduced to account for cracking, for other aspects that can be also quite complex, and equivalent viscous damping that account for different sources of energy dissipation. To overcome many of the limitations of linear analysis, we currently use nonlinear static analysis, what is also called pushover analysis. Pushover analysis provides the response in terms of capacity curve obtained by an incremental quasi-static application of horizontal loading to a nonlinear model. So in this case, we consider different analysis directions with a predefined load pattern, implying that there is a dominant translational mode, which is represented by this force distribution, and the response is essentially a single mode one. There are alternatives. We can use adaptive analysis, multimodal pushover analysis, but still with some, let's say, complexity in the application, and let's say losing some of the essential of the static procedure. The other, say, main characteristics is that the pushover analysis, monotonic analysis, is an incremental analysis in which we apply a load pattern and control the displacement of equivalent control point following the response of the structure to these horizontal force distributions. These characteristics is also explain also why we are normally requested to consider multiple force distribution and direction of analysis. In general, pushover analysis holds a significant number of advantages, and it is definitely a preferable method for a system like URM building, in which the nonlinear response is evident, is relevant since the beginning of the deformation. So this is something that we all have to consider, and we normally use this analysis method in many practical applications. We can use it also for design of new buildings. So you can use for is a simple framework to be used in the assessment of existing structures. It allows to account for several aspects that can really be analyzed and studied in a much more realistic way with respect to the linear methods, and also the degree of let's say additional safety you need in case of linear analysis, which you are comparing forces instead of displacements. You are comparing a linear response of a highly nonlinear behavior, which can be very different from single structure to single structure. These significant advantages of pushover analysis are there, but there are also some limitations for this kind of analysis. And the critical issues in the use of pushover analysis can be, for instance, summarized in these bullet points and a few slides later on. One is, the use of lateral load distributions. We select different lateral load distributions, and using different lateral load distribution, we may obtain different distributions of damage within the structure. And this represents an uncertainty in also for the engineer that reading this damage and with different damage predictions or damage concentration in different elements, considering the different load pattern, the different direction of analysis, then is requested to provide an intervention that is and cannot be really fully specific for a single record for a single analysis, but it is requested to provide an intervention to strengthen many and different peers, for instance, in a masonry building that possibly are not necessarily those involved in the real failure mechanism. Another aspect is the static approach, we use a nonlinear static approach, which allows to compute a capacity curve, which provides the evolution of lateral strength as a displacement of a control point is increasing. This is a significant advancement with respect to the linear approach. We directly deal with displacements which are definitely a better proxy of damage with respect to other measures. But again, we are dealing with simplified methods to compute the dynamic displacement demand, because we are not performing a dynamic analysis. We use a simplified rule comparing the activity of the system, the activity requested for an equivalent single degree of freedom structures. So there are several aspects that in a simplified way are accounted for in the analysis, and there are many proposals of reasonably working methods, but all simplified. Another aspect that needs to be considered is the effect of higher modes, and what is typically done is that the pushover response is somehow corrected by adding some coefficients, apply some coefficients, some forces that derive from the linear response to higher modes. This is not something typical, very relevant for low-rise masonry buildings, but in general, this is a point. And what is instead very common in the case of existing masonry buildings is the presence of flexible diaphragms, which can be timber floors and timber roofs. We know that codes and tools provide the way of using pushover analysis in case of stiff diaphragms, semi-stiff diaphragms, or very, very flexible diaphragm, in which we are allowed to analyze single walls instead of them part of a complete building model. And this is because the dynamic response of the different parts of the buildings is no more coupled, is not effectively coupled by the presence of a stiff diaphragm. And this is something that makes pushover analysis not easy at all in that case. Another aspect that needs to be treated outside the pushover, the classical pushover approach, is the topic of the assessment of slender cantilevering elements or local mechanisms, effects of contents that require the use of local models, but in particular they require the definition of an input by means of another response spectrum, which is not the response spectrum of the earthquake, but is the story response spectrum, which is filtered by the building response. Other cases of, let's say, controversial use of pushover analysis is the case of buildings with foundations at different levels, and or cases where soil-structure interaction is very, very relevant. In the case of different foundation levels, there are significant variations in stiffness and internal forces cannot be fully reproduced with a single pushover. We probably need to use different pushover analysis and check whether some simplification is appropriate. And in the case of soil foundation, in the soil structure interaction is relevant, we need to include in the model soil foundation models and perform dedicated analysis with flexible, deformable supports. This is something that we can do in the quasi-static fashion, but its actual representativeness would be in the time history, in the dynamic response. The other obvious intrinsic limitation is the one in which we perform monotonic analysis and tend to represent a cyclic response. Cyclic response implies cumulative damage, damage progression, strength deterioration, stiffness degradation, all aspects that cannot be fully reproduced by means of a monotonic analysis. And this also implies two different approximations that are not fully controlled. One is the amount of energy dissipation we actually have, and the other is the reliability of the lateral capacity we are assessing. Because the question could be, which is the actual lateral capacity? Because the cyclic response, depending on the loading history included in the seismic records, can be reduced, can be different in case of repeated cycles at different amplitudes. So if we think that these limitations are not negligible, if we think that in the case of the structure we want to analyze, we are not fully satisfied by linear analysis, of course, but also we are not satisfied even by a pushover analysis, we can resort to a more advanced method. It is nonlinear time history analysis, the more accurate and advanced method available so far in the representation of this specific phenomenon, which is nonlinear and dynamic. Advantages of nonlinear time history analysis are obvious. This method allows for the direct simulation of the structural response during the earthquake shaking. It does not require approximate procedures to estimate the seismic demand. You directly compute it. It does not require simplified or conventional approach to represent the nonlinear behavior of the damaged structure. We are representing it, we are modeling it. It overcomes the limitation of equivalent linear methods and overcomes the limitation of nonlinear static pushover analysis, which are less relevant with respect to the linear methods, but they are in some cases relevant. So for instance, it allows for the analysis of building with flexible diaphragm without any need for specific simplification. It does not require the definition of a predefined distribution of equivalent inertial forces. And if you want, it allows to directly include the vertical component of seismic motion into the analysis, into the incomplete building analysis. There are several aspects which are not trivial that need to be considered with care, with attention, when you use dynamic analysis in seismic assessment. In particular, the selection of time histories, which is the input of dynamic analysis, normally accelerographs, is a key aspect. In the past, this was one of the obstacles for the application of time history analysis. Then the other main obstacle was the lack of models which were capable of reproducing the static and dynamic nonlinear behavior of structures, particularly for masonry structures, with a combination of an efficient computational capacity of analyzing larger or complex structure within a reasonable time frame. This is particularly true for building models. And once these, let's say, technical aspects are fixed, then we need a procedure, a code procedure, which is guiding the identification of limit states and the approach to safety checks. This is something that typically is provided by codes, together with specific indications also to the previously highlighted aspects. Normally, codes specify that seismic input for nonlinear dynamic analysis can be provided in terms of accelerographs or group of accelerographs, meaning with group pair or triplet of accelerographs, depending on the number of components that are considered as relevant in the analysis. It is also considered that if you use a minimum of 7 groups of accelerogram, you can consider the average of the values, for instance, the displacement demand obtained in the analysis as an estimate of the demand to be compared with the capacity. And in the selection and definition of the accelerograms to be used for the nonlinear dynamic analysis, the codes require that these match a spectrum compatibility criterion. The spectrum compatibility is a criterion that provides the selection of a number of records which are close enough with the target response spectrum we expect for the specific site of the buildings where we are going to use the analysis. And the type of accelerograms that are considered are also different depending on their origin. In particular, we can use synthetic accelerograms, which are obtained through the complex geophysical, geomechanical, numerical simulation, which can include both deterministic and stochastic procedures to simulate the fault ruptures and then the seismic wave propagation within the soil media to the surface where the building is is located. One example of these tools for the generation of synthetic accelegrams is the SPEED program, the SPEED platform developed by Paolucci and others at the Polytechnic of Milan. This is clearly a very advanced methodology, but which requires expertise to be used, and that requires a lot of information also on the soil, and it is also somehow, let's say limited to deterministic analysis and deterministic simulations, which is very useful in many cases and specific cases, and justified for very relevant applications and structures. The other, say, older approach is the use of accelegrams, which are artificial. So they are signals generated from a target spectrum by means of stochastic algorithms. This is which are based on random vibration theory. For instance, the Gasparini-Van Marke algorithm is a famous one. We have to say that these accelegrams generated in this way are typically very rich in terms of frequency content and rarely they represent in the time domain something that is very similar to the natural accelegrams. The natural accelegrams is the, let's say, nowadays the obvious choice, because the availability of record during past earthquakes is very significant. There are various online databases. The seismic recording network is constantly enriched and extended and completed, and new records are recorded every day. So in these databases, we can find more and more records which can be selected to match the spectrum compatibility requirements. So the use of natural records is in general preferable. They are intrinsically more representative of the causality of the process from the generation to the recording at the site, and they present a realistic frequency content, a realistic duration. Realistic, they are real duration, even if they are recorded in a different location for a different earthquake, but they in the criteria that we can use for their selection, we can also consider not only the spectrum compatibility, but also the disaggregation of the main characteristics of the source, and with respect to the recording site. So this is something that is easily available in practice. We can count on several tools. For instance, the Rexel tool developed by Yerbolino and others within the Lewis consortium is a very significant a very simple tool to to perform this kind of selection. And then the model, because normally the codes, for instance, the Italian building code require that, okay, for performing nonlinear dynamic analysis of masonry structures, you need a nonlinear mechanical model with proven and documented effectiveness in reproducing the dynamic and cyclic behavior of masonry. Simple sentence, very complex to realize. But what we see on the right is really promising. This is a comparison between an experimental test and a numerical simulation of the test using an equivalent frame macroelement procedure, the Tremuri model. And to show the validity of a model, we need a validation. So the definition of validation is something that is an action in which you are checking or proving the validity of or the accuracy of something. And normally, to validate a procedure, to validate a modeling approach, you need benchmarks. We are normally used to deal with the experimental benchmarks, which are typically shaking table tests on reinforced masonry building structures. We have some examples in the plot that we can see in in the center and the right. See the top plots refer different stages of test of the house, which is reported in the central part of the slide. You see, this is a 2-story stone masonry house, full scale. Whether what we see in the right is a half scale structure, more complex representative of a building aggregate, a small building aggregate in historic center of a city, with some, again, capacity of the model proving its ability in reproducing the hysteretic behavior in a proper way, the cyclic dynamic behavior in a proper way. But okay, these are experiments. The groups of the researchers involved in the experimental test are the same involved in the numerical simulation of the test, so somehow may criticize this excellently performing modeling validation. And we then looked for some even more realistic and more independent validation. And the opportunity came from the Italian Seismic Observatory of Structures, which is a network of monitored structures, including 160 buildings, 7 bridges, 6 dams, which are spread over Italy in different seismic zones. And these monitored structures have recorded a number of earthquakes. And there is in particular one building, the Capuzzi School in Visso, in central Italy, in the Marche, built in 1930, and which was surveyed in 2009 and then fully instrumented in for the following vibrations to be recorded. The building is built in two parts: a main building and the partial structure. These portions A and B was checked after the 1997 earthquake. An intervention on repairing and strengthening intervention was performed on the structures, on both masonry walls and roof and floor structures. The scheme of the monitoring system installed by the Italian Civil Protection by the Structural Seismic Observatory, and this is so these are the examples of the instruments which are installed in the structures, starting from the basement to the different stories and the different positions to capture the main aspects of the seismic response. And we are very close to three of the epicenters of the main shaking of the central Italy earthquake sequence in 2016 and 2017. Actually, yes, these are the recordings of these events. As you can see here, these are the response spectrum of different stations for the records of different magnitude and epicentral distance that occur within the sequence. And in particular, you see that the events of October 26 and 30 were very close to the school, the Capuzzi School in Visso. And this is the damage that occurred actually in the structure. You see in plane damage, lot significant large cracks occurring in many of the piers. Basically, most of the piers were damaged in shear. It is a stone masonry pool. And then in a corner, we see in the picture on the left, we see the picture, the structure before the earthquake, and then we have the effect of damage with the building corner completely collapsed, at least of the upper level. And this is the internal damage. After the inspection, we have the collapse of the attic floor, and there are a lot of debris within the building. So we decided to try to simulate using the three-dimensional numerical model of the structure, modeled by the Tremuri program using an equivalent frame approach and a nonlinear macroelement representative of the cyclic response of piers and spandrels of the building, we adopted the measure properties derived from the in situ test, and when missing standard values from the Italian code. And then we implemented the floor and roof diaphragm models by means of the orthotropic elastic membranes that are represented in that are present in the Tremuri program. And we also calibrated the stiffness of the system to account for the nonlinear behavior under the strong motion input. This small calibration was actually based on the initial recordings that were performed in the dynamic identification of the structure, actually. And then we performed the sequential nonlinear dynamic analysis to consider, let's say, the effect of the main shaking affecting the structure. So in particular, those three mentioned in advance. So we could see not only the response to this the single shaking, but also the damage accumulation within the sequence. The adopted measure wall model is the classical nonlinear macroelement model implemented in Tremuri. We have the sequence of the images of damage after the Amatrice event in August, and then the very close ones in October, and in the Norcia at the end of October again. So in different walls where sliding shear and diagonal shear failure modes were observed. So with the initial stiffness of the orthotropic elastic membranes, we could hardly follow the response, but then after a calibration of the diaphragm stiffness, we could capture quite well the response. So in this case, you see that for most of the recording points, we have a very similar response with respect to the numerical, which is very close to the recorded one. And in terms of time history, the oscillations are synchronous and the peaks very close to each other. This also, in the end, implies that also in terms of hysteretic response, we could actually represent properly the response of the hysteretic response, the cyclic response, and this implies also the displacement demand is very close between the global response of the building during the real earthquake and the numerical analysis of on the structural model. Also, in terms of the form shapes, things are consistent. There is this wall in which we have a large damage prediction, and okay, we can follow quite well the response in the first two peaks. Then something happens in the model where damage is spread that is not allowing to fully represent the response of the building in the final part of the time history response, but still quite a significant achievement, as well as in this case, okay, there is a little shift, but in terms of accuracy in damage prediction and time history response assessment, again, a good result. As also it is the case in this case, in the case of this wall, where not only the approximate failure spread of damage within the wall is correctly reproduced, but also it is very well represented in terms of time history. The correct reproduction of the seismic behavior is also highlighted in this comparison of the recorded and numerical transfer functions, in which you see that at least the main frequencies and mean periods of the response are correctly calculated up to 0.2 seconds or slightly more. And we see another case in the y direction of the building. The first one was in the x direction. So in conclusion, on this validation, this comparison, we can see that this is a unique case of a full-scale existing buildings with a complex geometry, which was fully surveyed, which was retrofitted in the past after the 1997 earthquake, in which mechanical properties were derived from in situ test and complemented by information from the code, so a little uncertain in this part. These 11 accelerometers of the monitoring system were acting during the 2016 Central Italy earthquake sequence, and they recorded ground and floor acceleration in different points, and from double integration we could also derive the floor displacement. With respect to the experimental benchmarks we normally have in the lab, we have, let's say, from one side an uncertain, so let's say a partial knowledge on the structure, and in addition there are a lot of irregularities, scale effects, interaction between structural and non-structural components. For instance, there are non-structural walls in the building or other elements. There is the effect of material aging, which is somehow accounted for in the mechanical properties of the masonry walls, which was tested, but also there are other elements which are not tested. So this is a very realistic case, and the performance of the analysis were undoubtedly satisfactory. The key point was the calibration of the in-plane stiffness of the diaphragms, which was not available from the tests, and the equivalent frame approach for a regular wall configuration was extended also in this case, where, say, in general we had regularity, but not fully regular in all the elements of the walls. Some small irregularities were present, and the key point is that we could simulate these global response with an accurate dynamic time history analysis using a macro element which requires only a limited number of material parameters and material properties. You consider that there are less than 10, whereas there are more complex models available around that require maybe 20, 30 different mechanical or specific technological, phenomenological parameters to describe this behavior, where in this case we just need a couple of, let's say, elastic properties and a few strength properties, and that's it. This allows to reproduce global and local wall displacements, hysteretic response, damage pattern, and evolution of the dynamic properties with stiffness and strength degradation. So we can say that this model corresponds to the model required from the code, which was something that was valid for this kind of application. And the last point is the procedure for safety check, which is basically similar to nonlinear static analysis, a comparison between displacement capacity and displacement demand. In this case, the displacement capacity is, again, something that we can derive from a pushover analysis, and the displacement demand from the time history analysis directly. So we can summarize the steps that are required for the seismic assessment by means of nonlinear time history analysis. And these steps are the modeling of the structure with a model capable of reproducing its cyclic behavior, possibly with reasonable times of analysis, let's say minutes, not hours. Performing a model analysis to set the parameters of viscous damping to account for the small nonlinearities and dissipative phenomena that are not fully captured by this structural model. This means that these damping values need to be very small, not 5%, but maybe 1 or 2%. Nonlinear static analysis is then performed to assess displacement capacity at the attainment of specified limit states, and then we consider the site. For the site, we select the accelerograms, at least 7 groups, based on the site seismicity and the characteristics of the structure, and then we execute the nonlinear dynamic analysis and compare the mean displacement demand and the capacity associated with the different limit states. And that's it. Simple. I'm not sure, but I hope I have convinced you that time history analysis is something which is feasible, available, and can be used for specific applications that require something which is more than simply linear or nonlinear static methods. Thanks a lot for your attention.